Yeah, so hello everyone. Let's go through a fast review of what we saw in the last class, and then we continue. Please give me a second. Yeah, so we're focused on seismic data, and we're looking at this example of having an inline section of the subsurface, and we wanted to label the different phases corresponding to these different transitions in composition across the subsurface, which is relevant in the oil, gas industry, and so on. So we look at a very important architecture, the autoencoder, which is critical in learning this type of 2D data. There is image-alike. It's not exactly an image, but it's image-like type of data. But we are trying to extract abstract data. We know the input data could be that seismic section, section. And we do an encoding process where we obtain some vectorial representation called the latent space, the bottleneck, and that has a numerical description of that input data. Then we can reconstruct either back the same image, and we do that only if we are interested in the vector in the latent space, or we can reconstruct a different image that could be that actual phases level. So that would be like having just these numerical values at every point of the array corresponding to a label associated with each of the phases. So that's about the encoder. We're not going to review the layers today. We talk about the unit architecture, very important architecture. And now let's look at how we would actually run that script. That is the Keras script that would be done to learn from the data and to be able to predict areas that we didn't know before. So yeah, we're here just loading NumPy with very generic Python library, then the sequential for building the model. And then we load our data. It's being simplified here, but what is X, that would be my input array of elements, and those arrays are, an array of each of the sections, and the Y would be my corresponding reconstructed images. Could be exactly the same image, or it could be the levels, the phases as we just discussed. So then we reconstruct our model. Here the compile step is about, here we define something called the loss function, the optimizer, the accuracy, the metrics, and so on. We're ignoring that. We're going to see that later. But once we have that model, then we introduce our input data and output data, whether it's identical or not. And that would be a simple Keras script. This is okay whenever I don't have a lot of data. So what is the problem with this algorithm, with this code? That we are loading all of the data into the GPU for this training process. If we are running on GPU, for example, that would be putting everything on a GPU. And we don't always have all of those resources. Or maybe on the CPU still, we don't want to load so much data that uses all our RAM memory or the memory of the GPU. Then for that, there is another algorithm a bit more complex, where we use something called a data generator. So yeah, maybe this code is a bit extensive. So try to see at a high level and as I guide you. So basically, our keras script, that would be this one, would be in the main folder. We would have another folder containing the classes. An important class to mention here is the data generator. So another file, sorry, I said another folder is another file containing the classes. And the data generator is a key element that will load only what we need at a given time during the training process. So normally, the way these machine learning algorithms work is that they take a batch of data. That will be maybe 50 examples. Even maybe I have 150 samples in total. It takes first just 50. It does a training process and learns a bit about those 50 values and proceeds and take another 50, the subsequent 50, and then goes and with the other 50. And once it completes, it has completed an epoch, and that epoch is an iteration over the complete data. So the batch size is something that you can change in your algorithm, is how much you load at a given time. The data generator will allow you to load only that batch of data at that given time. So the way that is generally organized is, let's say here you can see a dictionary. You have a train, validation, and test set, just a list of names, and those names are going to correspond to your data elements that are going to be in another folder. So this would be your array in whatever format it is. Here is a NumPy type of data. It could be a different one. And then we have some labels. Yeah, just in this case is assumed to be a label, 0, 1. And it will not be the case that we have discussed yet, but we sometimes can have a prediction for the whole to the array. We're going to show how to change that algorithm to work with to the arrays. And then we have with outputs that can be added to the array. So the training generator uses the data generator that takes the partition, the training data, the output data. So just think of these labels as the output data, and the parameters that we have defined here. So this asterisk with a dictionary is the same as just introducing each of these parameters as an input, let's say, as an input in my data generator. The same, I apply the data generation to the validation set, and I get the validation set in the same way. We define the architecture. We discussed last week, yesterday, how we add the encoder, the decoder through a series of layers. And then we apply the, we're going to talk more about everything related to the compilation, but after that, you apply the fit method. Originally, we applied in the previous algorithm, we applied the fit method. Now we applied a very similar, this is called the fit generator method, where we are going to introduce this training generator and validation generator in a very analogous way, and some parameters for the processing, for the resources that I'm going to use during the optimization. Now, let's quickly look at that data generator. So the data generator is a class, and that class has a series of methods. I know there is a lot of things here for a slide. Don't worry too much about understanding every single detail. What we know is that at every step, where we are going to use only one batch of data in the process of learning about that data, this function is going to be run. So this method here, the fit generator, only call that method at a time. That method would call the data generation method another method. By the way, this is just an extension to try to put everything in a single slide. So this is this data generation is just another method. And in this method, the data is loaded. You can see here how each of the data is called by the ID, the name that was given to each of the elements. So if I wanted to make Y, the output data, to be exactly identical to the initial one, because I am only interested in the vector inside in the latent space, in that vector representation, then I just load the data again using the same algorithm. So my Y would be just identical to the X. Or I load another data corresponding, for example, to the fastest classification, and that goes in here too. So maybe just adding an additional element to the name, putting in the same folder or just changing the folder. Just make sure that the path is correct. And then you load the step by step, you're loading just a batch, and you go through all the batches of your data to complete an epoch that is one iteration of your whole data. Now let's talk slightly about about the optimizer, the loss function, the metrics. So we talk about the compilation step. So once you define the metric, the model, you apply a compile method. That compile method take your optimizer, take a loss function, and take some metrics. So the optimizer here, here's an example, and I know there is a lot of parameters here. These parameters could be relevant depending on the case. Important to notice here is the learning rate. The learning rate tells you how fast I am moving along a gradient. So the gradient is, the direction towards the bottom of the optimization surface that I'm trying to do. And the learning rate tells you how fast I am moving. If I am moving too fast, then likely the loss function is going to start moving, jumping all around. In that case, you decrease your learning rate and keep it low. Then you have a loss function. In this case, we're using the mean square error. That's good for optimizing continuous variables. Here's another example where I am using a binary cross entropy, which is more about classification of classification by of categories. I mean, this will be a binary category. And my metrics. Here we have only one metric. I have a list of them. Important metrics that we're going to see during the course is accuracy, precision, recall. And the loss function also can help you track your optimization process. And yeah, we're going to also see during the course things like L2 regularization, L1 regularization, when to use each of them, and some of these parameters that are a bit advanced, I would say. Now, you apply your fit function. You introduce your data, your validation data, you introduce your train data, and what we're going to observe is something like this. It's going to go step by step, epoch by epoch. I said that. So we have steps in which I am loading each how to go batch of data. So I'm gonna go batch by batch until I complete an epoch, which is an iteration over my whole data. And then it's going to print the metrics that you see here. So the interpretation of these metrics during the training process is very important. We have the loss function, which is supposed to go down. Oh, I didn't say that, but the loss function is a mixture of how much I am failing in the optimization. You want to decrease it. You want to decrease your error in the prediction. Sorry, in the prediction. So if your prediction is very good, it's perfect, that shouldn't always shouldn't be that perfect, but if it is perfect, you obtain a loss function of 0. But otherwise, you obtain a loss function that is very low. And then you obtain a loss function for the training set, and then another loss function for the validation set, and the same, an accuracy for the train set, and accuracy for the validation set. Now, what happens if you have an accuracy, very, very good accuracy on the train set, but that accuracy is not very good on the validation set? That can happen, and this is what is known as overfitting. If that is happening, your model is somehow failing. And that means your data has fitted somehow to the noise in your train set. It has found a way to relate that noise to what you want to predict. Obviously, that noise is not information, and that would fail entirely on the validation on the test set and anything else that you try. And this concept is called as overfitting, and I need to emphasize that because overfitting is one of the most misunderstood concepts in data science entirely, even by top data scientists. There is theories that the loss function is going to jump or something like that. That most of that is wrong. The only thing that you know, if your performance is very good on the train set at the end of the optimization, but it fails badly on your validation test set, then that is overfitting. And that's why it is important, but that's one of the reasons it is important to track these values during the optimization process. At the end, you save your autoencoder and you have your saved data. You save model, sorry. Now, another important thing is, you are running your optimization process. You don't know if something can fail. So you can always use model checkpoints, and that helps you basically save every time you're obtaining a model that is performing best. In this case, I define it to monitor my validation loss. If I obtain a validation loss that is lower than before, then save my model. And this is how a checkpoint model is defined and introduced in the callback as a function in my as an instance of this class model checkpoint in my method fit. Otherwise, you can, and you can load your model anytime using these. You first have to define the architecture of the model, then you load the weights. Yeah, so we talk about saving the model. And once you have done your optimization process, then you apply predict. You introduce your input data. Yeah, I'm just introducing an example of array, of two-dimensional array, and do a prediction, and that prediction should lead you to a reconstructed image. So if the reconstructed image is exactly the same, you re-obtain the same reconstructed image. But that's not what you necessarily are looking for. If you are reconstructing the same image, it's because you are interested in that latent space, that information, that description vector that is in the bottleneck that we are going to describe. What can we do with it? Now, let's look, for example, at one recent paper. This is 2023, 2nd of December. So it's very recent. And they have basically taken the unit architecture uh, as a foundation for classifying phases using about the same strategy that I have discussed here. They have made some changes in the architecture. Um, you don't have to understand exactly how they have done it, but this could be a nice paper to extract an initial model if you are building, if you are in a serious project. Otherwise, you can try the unit architecture and see how well it performs. And then they achieve amazing results. So here's an example of how the training data looks like. They have, again, these sections, same I have described, and they have the seismic, the phases as an output. They try, in this case, first, this is the actual prediction. Yeah, this is the truth value. So this is the classification done by the interpretation done by an expert. And then you have C, that is done using just the unit architecture. And it is not bad, but it still have, say, this area that is classified as the same as this fuzzy, for example. They make some additional changes to the architecture. They obtain this that looks closer to the interpretation done by an expert. And then they do their final solution. They implement their final solution that looks really, really amazingly close to the predicted solution. Now let's look at another paper. This is a bit older, and they do what is unsupervised phases classification. What it means unsupervised? So unsupervised, it means that you don't have an expert, at least not at the beginning, doing the classification. So it's not learning from a geophysicist. It is basically finding out how to interpret the data to extract those outputs. Yeah, so again, they obtain amazing results from this technique. Let me see. This is the top right. Um, Yeah, well, I think this one is a predicted is just looking very similar to the predicted one. So, but let's look at how exactly that works, because we have looked at how to train the autoencoder, but we have said that extracting the latent space is important to that because it has some description of the input image. So the goal of this unsupervised strategy is basically to make the algorithm itself recognize similarities between different areas in the surface and associate those similarities with a single fuzzy. So the way it is done is by getting that latent space representation as a vector description. And then subsequently, we're going to apply a clustering technique. And that clustering technique is basically associate similar areas of the section with other similar areas of the section. So here, basically, we have, as we defined before, an encoder. I'm using a very simple encoder with two dense layers, and a decoder using a very, again, a very simple representation. It doesn't matter this stage, it's just an example for you to visualize. And the autoencoder is built with that initial input. We introduce the encoded data and the corresponding decoded data and the corresponding decoder. So that's our model for the autoencoder. But we also get a second model, and that model would only involve the encoder. So it basically stops here and gets this encoder at this stage. So the input image is only processed up to the encoder instead of here, but where the processing is up to the decoded image. This is stopped at the encoded value to get basically the vector representation, the latent space. So the important thing is that after I have done my training, I have fit and compiled my input data, I can get those feature vectors by applying by applying the predictions on the input data. With those feature vectors, then I now have a better representation that is easier to work with for a subsequent cluster. Just can find if two of these vectors are similar, it means they have similar characteristics. Then we apply something called k-means, basically clustering by similarity. So we are now clustering that latent space, this vector space. So the latent space, so the data from the latent space is going to look like arrays like this, a series of vectors. Then we basically fit the input data. In this case, we're clustering, assuming that there is three centers. There's ways to control these parameters. We're not going to discuss this now, but and we obtain the labels. So every feature vector is now associated with a label. And that way we can associate different areas of these of this section with different phases. We do some clustering, so we cluster around some centers that are, where there is a strong concentration of vectors, and find out the optimum distributions of these phases values. So the result here is that we are able to classify that original data. And let's go to the autoencoder. So basically we took one section So we took the inline section as an input. We regenerated exactly the same input. We found out how to extract that vector out of the encoder. And then we use a clustering mechanism to cluster by similarity the different areas. So actually for this unsupervised method, we are it would be better to split this by smaller sections, smaller images, so we can actually find similarities between them. And then we use that to basically classify it. We classify these phases without the need of an expert. Now, this is not necessarily going to be really good. Maybe an expert is going to look at it and think, okay, it's kind of good, but there is some issues here. And that could be the starting point at which an expert who understand the interpreted data would decide the corrections for a subsequent labeling, and then you can proceed learning from the expert using, again, machine learning to do the final predictions. Now, there is a lot of things that we can do with the code architecture, which are not exactly the same as we have discussed. For example, let's say that I add some noise to the input image, and I keep the image as clean as it was at the reconstructed side. I add different types of noise, and I generate a lot of examples where I have some noise and I have some clean image. And I do and train this encoder-decoder architecture game. So this architecture is going to learn to clean the data. And that's the denoiser, for example. That's a way to construct a denoiser. There is also a way to basically have a latent space that has some kind of Gaussian distribution. These are called variational autoencoders. By changing certain parameters on that variational autoencoder, you are able to generate some input data, some sections similar to these ones, but that are not exactly real. So why would we generate data that is not real? This is called data augmentation, and it's done frequently in machine learning to have a large amount of data. So one of the issues that you have with data, this type of data, is that it is not present in enough amount to train really advanced algorithms. So you can do data augmentation using, for example, not only there is other options, but the variational autoencoder that also has the same encoder-decoder architecture, here containing that Gaussian distribution that we play with to obtain different variations of the original image. And do some data augmentation, generate additional data that is not exactly the original, but helps you improve your models for additional training. You can also does use Gaussian mixtures in your latent space and use that as a way to cluster without using that k-means extra process. And basically you cluster by based on uh, how the different elements of your section of your inline section go to the different Gaussian functions in your Gaussian mixture in the in the latent space. I know I'm talking about a lot of things. These are examples of things that we will look into during this course, and there is a lot of technical details. I know I have not covered things like data processing. There is also method for model selection when you have, and there is many techniques to improve these outputs. What else can you detect in the seismic data of this type? You can detect faults, salt tones, any features that the geophysicists are usually interested in extracting, as long if you have pre-labeled data by an expert that could be used to train the algorithm. And it could be trained in a loop way. So how the algorithm is learning progressively, and you the human is correcting the algorithm. So it could be what is called a human in the loop, where the human gives some information, the computer learns a bit more, and so on. What else? What other examples do we have? So, yeah. Well, we would also look at processing well logs. Autoencoders is one of the examples used for processing well logs, but we would go through reviewing anything from LSTM, how LSTM works, for example, which are the conventional algorithms, and we would review all the different methods and their applications, starting from non-deep learning approaches and where deep learning is really needed. Yeah, so at this stage, I think if you have specific questions about, I mean, I know I have not covered a lot of technical aspects. I wanted you to have a high level of the process at this stage, because that learning all the details takes time and requires steps. For example, pre-processing already involve data cleaning, involve normalization, and other techniques, and then selecting, splitting your data set requires a series of thinkings. How can you not have things like data leakage, for example? So that's all I had for this workshop.